So if you recall, when we talked about plane waves interacting with dielectric boundaries, we considered certain special angles, right? The normal incidence, the Brewster, and the total internal reflection. And in the normal incidence, we took the same two applications that we saw in the transmission lines in terms of the quarter wave transformer and the soap bubble colors, right? And I briefly described the way one would go about estimating the net reflection and the net transmission coefficients when we have two interfaces, right? And we saw that it was essentially sum total of infinite interactions between the two boundaries, right? And it converges to essentially giving us a net reflection coefficient and a net transmission coefficient at any given frequency, right? But rather than having to go through that trouble, I am going to say that with the scattering matrix theory that we have developed, we can actually look at the same problem in a much more elegant way. Okay. So let us consider a dielectric boundary between two media and normal incidence of plane waves, and this time I am going to use the wave amplitude definitions, right? Okay. So A or B is not really indicative of electric or magnetic fields, right? But instead they are these wave amplitudes whose square magnitude will give you the power flow in that particular direction shown by the arrow, right? So we have the wave impedance for the plane wave in each of these media given by, okay, okay. So remember that we had always chosen non-magnetic media. We'll do the same, which means that eta 1 is proportional to 1 over the F index, right? Eta 2 is proportional to 1 over N2. Okay. So S11 is essentially B1 by A1, right? And this we said was E1 minus divided by square root of 2 eta 1 divided by E1 plus by square root of 2 eta 1. Since the wave impedance is the same in a single port, in a given port, right, the two denominators would cancel. But remember, in general, the port impedances can be different. They all don't have to be the same, right? In fact, in medium 2, the wave impedance is different. So we'll see that S12 and S21 will actually have different impedances. Okay. Remember, it is defined with A2 being 0. So I'm not launching another plane wave from the second medium. I'm just launching a plane wave from medium 1, which is denoted with A1, and I'm asking how much of it is coming back through B1, right? But this is essentially our reflection coefficient, right? So we can say that this is eta 2 minus eta 1 by eta 2 plus eta 1. This actually transforms to, because they are inversely proportional to indices, we'll get n1 minus n2 by n1 plus n2. Okay, and we'll call this small lowercase r, right? So we are noticing that there is a relation between the scattering matrices and the gamma t, but we should not say that they are the same, right? In some situations we may find relations between them. Okay. So similarly, S22 is B2 by A2 given A1 is 0, right? We know that this is just minus of gamma, right? And this happens to be N2 minus N1 by N2 plus N. Okay, so this we can say is minus R. Okay, then we have S12, which is B1 by A2 given A1 is 0. Okay, so this time I am launching a wave from medium 2 and I am asking how much is getting transmitted through, right? So remember that this was E minus in medium 1 by square root of 2 eta 1 divided by E2 plus divided by square root of 2 eta 2, right? So we actually have a square root of eta 2 by eta 1 multiplied by, so E1 minus phasor and E2 plus phasor, that's essentially the transmission coefficient, right? So we can say that this is 2 eta 1 divided by eta 1 plus eta 2. Right, how did I get that? Remember that I am just using the relation. Whenever I want capital T, I just think of the relation 1 plus gamma. There's another relation also that we got from the boundary conditions, but this is one that elegantly that one can remember, right? So going from medium 2 to 1, right? So this was the reflection coefficient we got. So I just take this and add 1 to it, and that is what I plop here, right? So I notice that I get an expression 2 square root of eta 1 eta 2 divided by eta 1 plus eta 2. This also looks the same for the index case 2 n1 n2 by n1 plus n2. We'll call this some t prime. Okay. Actually, we can just call it t, not t prime. Okay. So the last of the S parameters is S21, which is B2 by A1 given A2 is 0, and we'll notice that you can go through the same mathematics, right? You will find that it is exactly the same. Okay, so we can say that this is also t. Okay, so this is certainly a lossless two port, right? So we can actually use the power conservation here on the lowercase r and t. So what will that say? So power conservation says mod of S11 squared plus mod of S21 squared is equal to 1. right? Which is to say that S11 squared is R squared plus S21 is T squared is equal to 1. Okay. Remember, R and T are different from gamma and capital T. Right? Gamma square plus capital T square is not 1. Right? We saw that from our discussion on power conservation. But now that I am defining these wave amplitudes, right, which are sort of like the square root of power, the power conservation falls out as simple identities, right? So what can we say is the S matrix for a plane wave that is interacting with a dielectric medium? S is equal to S11 is R, S22 is minus R, S12 is T, and S21 is also T. Okay, so we've actually created a S matrix that relates the wave amplitudes from the left hand to the right. Okay, so using the relation that we derived just in the last slide, we can also go into the T matrix formalism, right? And we can say that it is 1 over T, 1, R, R, 1. Okay, so we have the T transmission matrix and the scattering matrix for an interaction with a dielectric boundary. Let us look at propagation through no discontinuities. So I just have a plane wave going from point A to point B of some distance, right? So we can even look at that as a two-port device, right? Where I have launched a wave right, and there's no coupling between A2 to B2, right? So whatever plane wave I launch at A2, because there's no discontinuity, it's a homogeneous unbounded media, I just expect A2 to just move to port 1 and show up as B1, right? So it's just going to be a phase delay that we can think of. So we can also think of this as a delay element, right? Okay, so we can simply say that B2 is A1 e to the minus j beta. Let's say that this length is L. Right? So beta is the propagation constant, right? So again, this formalism is very general, right? It could be voltages and currents on transmission lines, it could be modes in rectangular waveguides, right? Or it could be plane waves in a unbounded media, right? For all of them, you can use the same matrix formalism. Similarly, we can say that B1 is A2 e to the minus j beta L, or we can say that A2 is B1 e to the plus j beta L. Right. Whether it is for the T matrix or the S matrix, you can just swap the order of A2 and B2, right? So we actually get a very simple S matrix. So if I am looking at the scattering matrix, I actually just get 0 e to the minus j beta L e to the minus j beta L 0. Okay, so this is my S matrix, and if I want my T matrix, you can of course use the relationship, but since it's such a simple one, we can actually quite trivially write it down. Okay. So just with these two, right, we can actually do some very powerful work, right? So let us look at that. So we are going to revisit the layered media. Okay, so I have medium with refractive index N1, N2 and N3, right? In the case of a soap bubble, it was air, soapy film and air, right? So N1 was equal to N3, right? And we also looked at the case of the quarter wave transformer, right, where I would want N2 to be the geometric mean of N1 and N3, and it would have to be precisely quarter wave thick, right, where the wavelength is the wavelength at which I would like to reject reflections for AR coating. So we saw this in the context of AR coating. We'll revisit that, and now you can actually exactly calculate this reflection, net reflection and net transmission, right, using the scattering matrix formalism or the transmission matrix formalism. So what I'm going to say is there's A1 and B1. Let's call this B1 prime and A1 prime. A fictitious port that is inside medium 2, right, with index N2, because what I measure is the net reflection and the net transmission, reflection into medium 1 or transmission into medium 3, right. But I can break these into three individual two-port components. Okay. So I can consider the first interface from medium 1 to medium 2 as one transmission matrix, and then there is the free propagation of a plane wave through medium 2 from one boundary to the other of a finite distance, let's call it L. Okay, and then I have another transmission matrix for the second interaction of a dielectric boundary, right. So if I were to take these individual transmission matrices, multiply them together, I notice that I can get the net response, right, and this should actually be the same behavior that we expected from having to include multiple round trips, right, and multiple reflections across these boundaries, and taking a summation, right, of this convergent series and estimating the net reflection or transmission. Okay. So let us call these interfaces as A and B, right. We can actually say that the net transmission can be given by the transmission matrix for the interaction of the dielectric boundary at A multiplied by TD, D standing for the delay, right. So I'm going to say that there's a delay transmission matrix for the plane wave going from interface A to interface B, right, and then I can multiply that with TB, right. So TA relates A1 B1 to A1 prime B1 prime, and TD relates A1 prime B1 prime to A2 prime B2 prime, and TB relates A2 prime B2 prime to A2 and B2, right. So in sequence I can just relate all these unknown variables through these transmission matrices, and I can get one composite or net transmission matrix that can relate the A1s and B1s to A2 and B2, right. So you can actually write this as 1 over T 1 2 subscript 1 2 saying the transmission T going from 1 to 2, right? The T value that we estimated during the scattering matrix formalism. 1 R12 R1, and then we have the T matrix for the delay. Then we have 1 over T23 1 R23 R23 1, right? So if I were to give you the values of indices n1, n2 and n3, you can actually estimate these r's and t's, and given L, and also you can estimate beta. You know all the parameters that are in the matrices. You can simply multiply these, right, and you can actually get the net transmission matrix. And if I were to ask you how much was the light that is reflected back, right, which is what we looked at, which is just the ratio B1 to A1, which is the scattering matrix S11, right? And if I wanted the power reflected back, I need mod S11 squared, right? So once you know the net transmission matrix, you can go to the scattering matrix formalism, look at S11 and take the modulus square of it, okay? So at this juncture, I would like to implement this simply by code using some commercial software. I have used Python here. You are of course welcome to use any software you like, for which the syntax you are very comfortable with, and you can just walk through with me, right, in writing this basic script for looking at the reflection from two dielectric boundaries, right? And we'll actually look at the spectrum. We'll look at a very specific example of creating an AR coating film for solar cells, right, which are typically made out of the silicon material, and we will try to see how we can script a basic code piece of code that will be able to estimate what is the net reflection coming off of the solar cell by applying these anti-reflection coatings on top of them. Okay, thank you.